like to thank the organizers for giving me the opportunity to present my work here. I will talk about probing the electromagnetic field with charge dependence of directed flow in star experiment at RHIC. So I will start with the magnetic field in heavy ion collisions. In non-central heavy ion collisions, that is the collisions with non-zero impact parameters, there are charged spectators that do not take part in the collisions, and they just fly along the beam direction. Since they are charged, they produce electric currents. So the produced electric currents are like two parallel current carrying wires, where the currents are flowing in the opposite directions as shown right here. This huge current can produce magnetic fields from the theory of electrodynamics. So in this case, the magnetic fields due to these two sources basically adds up. We can easily estimate the produced magnetic field in heavy ion collision. Here is the crude estimation of the produced magnetic field in the heavy ion collision. In gold-gold collisions at RHIC, at 200 GeV with the impact parameter B equals to 5 Fermi, the produced magnetic field is of the order of 10 to the 18 Gauss. So how this magnetic field strong or weak, we can easily estimate that just by comparing the existing magnetic field that exists in our universe. So it's like for Earth, the magnetic field is 0.5 Gauss. In star experiment, the star magnet has like 5,000 Gauss magnetic field. In neutron star, especially the magnetar, the magnetic field is 10 to the 14 Gauss, but in heavy ion collision, is of the order of 10 to the 18 Gauss. So this is the strongest magnetic field ever produced in the laboratory. So this strong magnetic field has observable effects on the properties of produced particles, such as anisotropic flow, and this is why this have been like, there are many interests among theorists and experimentalists nowadays. So I would mainly focus on the directed flow and charge splitting that is caused by the magnetic field. The anisotropic flow are the important observables to characterize the heavy ion collisions, and it can be expressed in terms of Fourier decomposition of final state azimuthal particle distribution, as shown by the expression right here, or the different flow coefficients, different Fourier coefficients are called the flow coefficients. Vn for directed flow, this is the first order harmonic coefficient V1, and V2 is the elliptic flow, and so on and so forth. V1 basically produced at the early stage of the collision, and they can probe the strong electromagnetic field. How this electromagnetic field can give the splitting in V1, I have tried to explain a little bit here. Suppose we have a non-central heavy ion collision. The collision occurs along the z direction here, and x-axis shown here perpendicular to the z direction is the impact parameter direction. So the plane that defines the x-axis and z-axis defined by this by x-axis and z-axis, the plane is called the reaction plane, and the produced magnetic field is perpendicular to this reaction plane. Now, this produced magnetic field have several consequences. Let's talk about the Hall effect. In such collisions, the medium is produced, and the produced medium has a longitudinal velocity along the beam direction. Here, the magnetic field produced is perpendicular to the beam direction, that is along the y-axis. So the Lorentz force pushes the positively and negatively charged particles in opposite directions. So this basically generates a current that is perpendicular to the direction of magnetic field as well as the initial velocity direction. So this is Hall effect. Not only that, there are also important effects like Faraday and Coulomb effect. As the spectators fly away along the beam direction, the produced magnetic field decays down very fast, and this time-varying magnetic field can generate electric field. This is a Faraday effect. On top of that, the charged spectators can also generate the Coulomb field. So this will also have an effect on the produced particles. Now, in reality, all these effects are present in experimental scenarios. So I have tried to put all these effects in a single diagram. I know it's a bit complicated, but let me explain here a little bit. Here you can see I have shown the currents due to Hall, Coulomb, and Faraday effects, and they are kind of competing effects in this case. I have also shown the direction of the V1 for positive particles in negative rapidity as well as positive rapidity. The direction for V1 for negative particles would be in the other way around. So it's implied that electromagnetic field could drive the V1 splitting between particles and antiparticles. But now the most interesting question is, like, can we measure this splitting in experiment? Well, we can measure this splitting in experiment, but we have several challenges in experiment. The main challenge is this transport phenomena. By transport phenomena means during the collision, the up and down quarks from the beam rapidity can be transported towards the mid rapidity. So the beam rapidity quarks, like the transported quarks, U and D quarks, travel from the beams. So they have different interaction than the produced quarks because they suffer a lot more interactions than the produced quarks. So the transported quarks have different V1 than the produced quarks. So if we measure splitting between a quark that is transported and an antiquark that is purely produced, that can give you the splitting due to this transport phenomena. So this kind of splitting interferes with the electromagnetic field-driven splitting, and it's very difficult to isolate in experimental measurements. How this transported quark effect interferes with this electromagnetic field, I have tried to explain in a very qualitative way. Here I have shown the expectation of this sign of the splitting between proton and antiproton with centrality. In the left-hand cartoon here, I have shown a model expectation, URQMD expectation of this sign of the splitting between proton and antiproton when there is only transported quarks. So only for transported quarks, this sign of the splitting is positive, but when there is only magnetic field in the system, in the middle panel, the sign of the splitting between proton and antiproton is negative. But when both the effects are present in the system, like in real scenario, the overall effect could be something like which has been shown in panel C. So we can see positive as well as negative sign of the splitting depending upon which effect is dominating. So we can always look for the negative sign as a sign of the electromagnetic field effect in experimental measurements. But we can look at the experimental results. But before going there, I would like to discuss an approach that really subtract the effect of the transported quarks. The motivation of this approach is like, since in experiment it is impossible to distinguish between produced and transported U and D quarks, we can always avoid the particles that contains U and D quarks. So by avoiding particles that contains U and D quarks, we ended up with 7 produced particles that are basically measured in experiment abundantly. So the 7 particles are antichaon, antiproton, anti-lambda, phi, cascade bar plus, omega minus, and omega bar plus. Now the approach tells us with these particles, we can make a clean case to measure the electromagnetic field-driven splitting. How do we do that? We combine different particles like this and compare the combination with the same mass at the constituent level. But here is a catch, like whether this combination are like the process of combining particle and comparing them is a right way or not, there is a way to test it. So we can test it using the quark coalescence scenario. We use the coalescence-inspired sum rule. The coalescence-inspired sum rule is basically V1 of a hadron is nothing but the summed V1 of its constituent quarks, but that should be measured in the same rapidity and transverse momentum over number of constituent quark phase space. We have tested this coalescence sum rule first with the identical quark combination. How do we get the identical quark combination here? Look at this cartoon here. If we combine antichaon with anti-lambda, we have 2 U bar, 1 D bar, 1 S, and 1 S bar quarks. On the other hand, if we combine antiproton with phi meson, then we also have like the same identical quark content. So in experiment, we can measure the left-hand side of this equation and the right-hand side of this equation and can see whether they are same or not. If they are same, then we would say like the coalescence sum rule holds in experimental measurements. But in this case, we have charge difference 0, strangeness difference 0 between left-hand side and right-hand side. Now, the approach tells to move on and make further combinations with those produced particles. But in this case, we will have non-zero charge difference and non-zero strangeness difference. Here I have shown an example. Like here I have combined the anti-kaon with the 1/3 of anti-proton and compare with the anti-lambda. In this case also we have to keep in mind that the quark level mass is same for all these combinations. But in this case we created a charge difference which is 4/3 and the strangeness difference which is 2. In this way we can make many combinations. So here I have shown like the 5 combinations. All these combinations are free from the transported quarks. These 5 combinations are really independent combinations. We can see we have 2 degenerate combinations having same delta S equals to 2. These 2 combinations are basically used for cross-checking. But the main motivation is to measure all these 5 combinations in experiment and measure the splitting as a function of delta Q and delta S, because we have many different delta Q values for all these combinations. Now moving towards the measurements, before going to the experimental measurements, I would show you the star detector setup here. So this is the star detector setup. The main central barrel detectors are time projection chamber and time of flight detectors. This TPC, time projection chamber, and time of flight top detector are used for the particle identification. TPC measures the energy loss of tracks within the selected rapidity region, in mid-rapidity region, and top measures the time of flight of the particles. We also use the event plane detector and GDC, the 0-degree calorimeter detector, which is situated in the forward rapidity region to measure the reaction plane. The data sets analyzed for these measurements are gold-gold collisions at beam energy scan 2 at 27 GeV, then gold-gold collisions at 200 GeV, and also the isobaric collisions at ruthenium and zirconium. So here is the result for testing the coalescence sum rule at 27 GeV. On the left-hand side, I have shown the delta V1 as a function of rapidity. The delta V1 is the V1 difference between left-hand side and the right-hand side. In the right side plot, here I have shown the same, but as a function of PT over NQ. Look at this left side plot. Here, we have seen that the extracted slope for this delta V1 is of the order of 10 to the minus 4. So the sum rule basically holds within the measured uncertainties. Now move on to the non-zero delta Q case. Here delta Q is equal to 4/3. In the left-hand side, this is the delta V1 as a function of rapidity, and the right-hand side, the delta V1 as a function of PT over NQ. The most interestingly, for non-zero delta Q, we have a larger value of the splitting the delta V1 at larger rapidity as well as larger PT over NQ. We have also compared with a model that has no electromagnetic field, and we can see that this model has just the opposite trend as seen in our data. Here is the splitting with charge and strangeness. Here I have shown, like in the first panel, the panel A and panel C, the splitting as a function of charge difference and strangeness difference measured at gold-gold collision 27 GeV. In the bottom 2 panels, I have shown the measurements at 200 GeV. The measurements are fitted with a linear function. Here we assume that the fit is constrained within 0. The most interesting observation here is that this delta V1 slope increases with delta Q as well as with delta S. We can also observe that the splitting increases going from 200 GeV to 27 GeV. This is due to the longer persistence of electromagnetic field at lower energy. We have also compared the measurements with AMPT model. You can certainly see that AMPT cannot describe the data. We have also compared the measurements with Parton-Hadron string dynamics model that includes the electromagnetic field. This can definitely describe the data within error bars. You can see this greenish band here. But I would like to make a comment here, like the electromagnetic field effect is not only the sole difference between these 2 models compared here, like AMPT and PHST. So the splitting shown so far was based on the species with produced quarks only. Here I would show you the splitting between proton and antiproton in 50 to 80% centrality. In the upper panels, I have shown the V1 for proton and antiproton for 200 GeV gold-gold collisions, ruthenium-ruthenium, and zirconium-zirconium collisions, and also at 27 GeV gold-gold collisions. In the lower panels, I have shown the delta V1 between proton and antiproton as a function of rapidity for these different collision systems and different energy. We have extracted the slope of this delta V1 measurements between proton and antiproton, which is a negative with more than 5 sigma significance. And this delta V1 for 27 GeV is much, much stronger than 200 GeV. Now, let's move on to the next slide. Here I have shown the splitting between particle and antiparticle with centrality for different collision energy and different collision systems. For proton minus antiproton, we have shown with the red markers. For kaon antikaon, we have shown with blue markers. For pion antipion, which we have shown with the black markers. The interesting observation here is this delta dV1 dy, the sign of the splitting, decreases as we go from central to peripheral collisions, and the measurement has more than 5 sigma significance. This negative sign of this delta V1 splitting as a function of centrality, mostly in the peripheral collision, agrees qualitatively at least with the expectation of the electromagnetic field, where Faraday plus Coulomb effect dominates over Hall plus transport effect. So this brings me to my summary. So for summary, I would say we measured the charge and strangeness dependent splitting from, which is free from the transported quark effect. This splitting increases with charge and strangeness, and we have seen the splitting is stronger in lower collision energy. We have compared PHSD, including electromagnetic field calculations, to describe the charge-dependent splitting, and we have found like measurable agreement within the uncertainties. The negative slope of the splitting between particles and antiparticles in peripheral collisions, we have seen this, and it qualitatively agrees with the expectation of electromagnetic field, where we found that Faraday plus Coulomb effect dominates over Hall plus transport. So that's all from my side. Thank you.
Thank you very much. Questions?
Thank you, Ashik. Very nice talk. Can you go back one page? Yes. So I see that you have results for 2 different energies, and that the strength of the signal is pretty much the same in both energies for gold-gold. I wanted to ask you, is there a way to extract the intensity of the field from your analysis?
Well, this is a very interesting question. So basically, first I would make a comment for your first comment, like the strength of the splitting for different energies is the same. I think for 27 GeV, it's multiplied with 0.2. So it's not the same.
Okay, so there's got to be a way of
exactly.
mapping the strength with energy. What, can you extract the strength of the field?
Well, so this is a very interesting question, basically. But we can extract the magnetic field strength and also characterize these produced QGP medium, like electrical conductivity and all that. But we need some theoretical model to constrain this.
I'm trying to understand interpretation of one of the statements that you're making, which is also on this page. It says that Faraday and Coulomb effects are dominating. The way I read that is that the magnetic field is decaying very rapidly because of the Faraday law. So again, it may be in the same direction. So between Faraday and Coulomb, can you still say which of the two dominates, or they're equally powerful?
Well, so it is very, very difficult to understand. I mean, it's very difficult to say whether Faraday is dominating or Coulomb is dominating. But based on a naive hydro with electromagnetic field calculation, like I have shown here, like hydro plus electromagnetic field calculation, if we assume Faraday and Coulomb component are dominating over Hall, then we should see this sign of the splitting is something like that. But if Hall effect dominates over them, but the sign would be then the other way around. But to answer that question, your question, we really need to look for this sign in experimental measurements. But so far, we have seen like for peripheral collision, the splitting is negative, and at least it is fitting with this qualitative argument of these calculations.
The reason this might be important is that, of course, Coulomb effects, nobody doubts that it might be very large there. But if there is also very large Faraday effect, it kind of means that you are going to have very rapid decay of the magnetic field and perhaps no chance for CME.
Yeah, and also I think I would like to add a comment here. Like the point you made like is very important for beam energy dependence. Like at lower energy, you will have longer persistent electromagnetic field compared to the higher collision energy. So it's very important to look at for different collision energy, especially at lower energies.
Okay, I'm trying to understand this physics. I am not really from this field, but I'm really very confused, I should say. So my point is, at least as I know, when you have very central collisions, usually nuclear forces dominated from column already, but now you are saying that central collisions produce very high magnetic fields. So the scales need to be compatible, I don't know, these magnetic fields. And if they are so strong, as you said, you should see in particle and antiparticle much easier than seeing chiral balance. That's much more sophisticated because it needs chiral symmetry and a lot of things. So I like your proposal, but so at the end, what you say is you can really distinguish this particle and antiparticle production by really electromagnetic effects and not only also, so you don't expect any nuclear effects on this case, only for me to know.
Well,
Yeah.
so,
because I think it's much, should see, or if don't see, they decay very fast. If they decay very fast, no effects. You cannot say that you have a long field if it doesn't remain. So it doesn't matter. So I'd like to understand, so I don't know if my question was
yeah, okay.
okay.
So let me make sure
Very
that
confused, I should say.
let me make sure that I understood your question first. So you mean like the splitting I am seeing here and interpreting the splitting as an effect of electromagnetic field is not like due to the chiral imbalance or anything else, right? But like the previous speaker, Gan, told about the CME, but CME is not perpendicular to the magnetic field. It's along the direction of magnetic field, the chiral separation. But in this case, like what separation we are measuring here, this is perpendicular to the magnetic field. So it cannot be due to this chirality. So, yeah.
But can you say that all, okay, more or less the same?
Yeah, and also like it's very.
Effects, if I understood that, considering as static effects, because of the sacks. So this question that involves the column is more important than Faraday.
Mm-hmm.
You don't know.
Yeah, exactly. This is very. I think this is a debatable issue, like which one should dominate, and it's entirely depending on the lifetime of the magnetic field and the strength of the magnetic field as well, because this is very emerging field now, and everyone is looking for the answer.
Let's thanks the speaker again. So now it's lunchtime. We have to be back at 2.